We're ready now to start our chapter about circuits. We've already done some simple circuits with a capacitor and multiple capacitors. Now we're going to layer in circuits that include resistors. Circuits are really important to study because we live, maybe especially more so now than ever before, we live in an electronic world. I'm sure if you just glance around you, you can probably see dozens of things that have circuits in them. So we're going to look at how some of those things start to work. We'll start with some more basic analysis, and then we'll ramp it up to do some more detailed things with even more components. Let's define all of our elements of a circuit now, and the symbols we use to draw them in diagrams. So first is our battery. A battery is something that supplies potential to a circuit. The potential of a battery can be written as V or delta V or epsilon. So those are the three things you might see. They all stand for potential or potential difference or electric potential difference or just plain voltage. Okay, next we have a wire. With wires, the first thing we do is we assume they have a resistance of 0. Of course, that's not perfectly true, but it's close enough to true when you have other things with bigger resistance in the system. So we assume they have a 0 resistance. The other thing that's really important to remember about wires is that they're bendy. So when we draw diagrams, we tend to draw wires with straight lines and sharp corners, but it doesn't have to be like that. Just imagine a piece of wire. So it can be bent into any shape you want it to be. The next two things we have in our pictures are resistors and light bulbs. So these are things that dissipate energy. A battery puts energy into a system, a resistor and a light bulb dissipates the energy, comes out of the system. A resistor has a little squiggly or a zigzag line. A light bulb is a little circuit with a loop-de-loop in it. Sometimes we would also just draw light bulbs the same thing as a resistor. It's kind of your own preference, doesn't really matter. Okay, next we come to a junction. A junction is a place where wires meet. And of course, the important thing we're going to think about at junctions is that at a junction, this is a place where a current can split off. It can go one of two paths. And we have capacitors, which we've already met. We know that capacitors store up energy. And the last circuit element we'll use is a switch. We can open and close switches. When switches are open, that's this picture right here. When switches are open, current can't flow because there's a break in the wire. If a switch is closed, our element looks like this. Dot here to show the closed switch. When the switch is closed, the current can flow because we have a complete circuit. So these are the circuit elements we're going to be working with. Next, we'll move on to drawing circuit diagrams. Let's put a bunch of elements in a circuit. Let's connect a battery, a resistor, a light bulb, an open switch, another resistor, and a capacitor. Let's connect those all in a circuit and let's draw the circuit diagram. Let's start with the battery. So the battery is represented by two lines. The long line is the positive end. The short line is the negative end. Our battery has an amount of potential that we might call delta V. Then we have a wire that goes up to the first resistor. That's a zigzag line. Let's call that R1 just for the first resistor. Then we get to the light bulb, which is a circle with a little loop-de-loop in it. I don't have a symbol for a light bulb. I'm just going to spell out light bulb. Then we come down, we come to a switch. We see that this switch is open, so I'm going to draw it as an open switch. Come down around the corner, back to a second resistor. Let's call that second one R2. Then we have a capacitor, which is our two lines. Normally a capacitor is a C, and then we come back around to the battery. So there's a full circuit. With our switch, in the one that we have drawn right now, our switch is open. So if the switch is open, there's no current flow. If we flip the switch and make it closed, there will be a current flow. So this is a general circuit with lots of elements. First, we're going to focus in and look at just resistors for a little bit, and then we'll come back to combination circuits. Our simplest resistor circuit would be a single resistor connected to a battery. And a resistor is a circuit element that dissipates energy. In general, we use it to control the current. What do we know here? If your battery has a potential delta V, then the potential across the resistor will also be delta V. Okay, so the energy put out by a circuit gets used up by the circuit. Most of our resistors will investigate our ohmic materials, which tells us that delta V equals IR. The current through the resistor times the resistance will give us the potential across the resistor. So Ohm's law, we're going to treat all of our resistors as ohmic, so Ohm's law will apply to all of our resistors. This, of course, is the simplest circuit. We rarely just have a single resistor in a circuit. Normally, we have multiple resistors in a circuit, and we'll look at how to deal with those next. One way to connect resistors, multiple resistors, is to connect them in series. A series connection is the same with resistors as it was with capacitors. It's when they're connected all in a line. So resistors connected in series are all joined in a line. If they're all joined in a line, it means they all have the same current flowing through them. You can see that when you look at what happens when we hook up the circuit. So we put a battery in. We know that the current is going to flow out of the battery from the positive end. The current will stay in the wire, will come down around the turn, go through the first resistor, come on down, pass through the second resistor, down through the third resistor, keep coming back around till it goes back into the battery. So all three of those resistors have the same current. So resistor R1 has current I, resistor R2 has current I, and resistor 3 has current I. So a series connection has things with the same current. So all of those have the same current. What we can do is we can create an equivalent circuit where we take out our three resistors, put in a new resistor with a single resistance that draws the same current. So an equivalent circuit has the same potential of a battery, has the same current I, but it has a new resistor with a value of resistance called R equivalent. So we can replace that circuit with an equivalent circuit. And this is similar to what we did with our capacitors. And our equivalent circuit has the same potential, the same current, but the resistance is now called R equivalent. So the current that comes out of this battery is I, comes all down around, and back in. Okie dokie. So let's see if we can get a relationship between these two circuits and how do we relate the equivalent resistance to those individual resistances. Well, what we know about the potential is that's the energy put into the circuit. Whatever energy is put into the circuit has to be used up by the circuit. So the potential supplied by the battery has to be distributed across the three resistors. And since we're assuming the wires have no resistance at all of the potential is distributed across the three resistors. So that tells us that the total potential put out, delta V, is the potential across the first resistor, delta V1, plus the potential across the second resistor, delta V2, plus the potential across the third resistor, delta V3. Here's where we remember Ohm's law. Which says that delta V, whoops, I said V, but I wrote I. Delta V equals I times R. So for our three potentials, delta V1, delta V2, and delta V3, we've got I times R1 plus I times R2 plus I times R3. For our net potential, delta V, let's look at our equivalent circuit. On our equivalent circuit, delta V equals I times R equivalent. Okay, let's put that in on the left-hand side of our equation. What we notice here is that we have an I in every single term, so we could divide both sides by the current I, and we're left with R equivalent. So the equivalent resistance for a set of resistors connected in parallel is R1 plus R2 plus R3. So this is how we add resistors in series. Next, let's do an example of a series connection of resistors.